In the earlier slides, we learned about Daubigner's triads and Newland's law of octaves. In Daubigner's triads, we saw that Daubigner made groups of 3 elements having similar chemical properties. And in the Newland's law of octaves, elements were arranged in the increasing order of their atomic masses, and they arrange themselves in seven groups. The properties of elements repeated after every 8th element. Today we will learn Mendeleev's periodic table. Mendeleev showed a relationship between atomic mass and the chemical and physical properties of an element. So he showed a connection between this atomic mass, the physical and chemical properties of an element. Now, what is atomic mass? Atomic mass is the mass of an atom. Example, when you have hydrogen, hydrogen has atomic mass 1 AMU, which stands for atomic mass unit. Just like you have kg and grams, atoms have a special unit called atomic mass unit. Like carbon, the mass of one carbon is 12 AMU, 12 atomic mass units. So every atom is related with a mass, has its mass. And then we have the physical properties. The physical properties are like the boiling point, the density, the color, the melting point. So we have boiling point, maybe the melting point, we have the density, the color. These are physical properties. And chemical properties is how elements react with other elements. So this was the basis of Mendeleev's periodic table. He showed a relationship between atomic mass, the physical and chemical properties of an element. Dmitry Ivanovich Mendeleev was a Russian chemist. He was the most important contributor to the early development of the periodic table. Now, during Mendeleev's time, when Mendeleev started his work, there were 63 elements discovered. So what Mendeleev did, he took each of these elements and combined them with oxygen and hydrogen and found the formula of its oxide and hydride. So the element was taken, it was then made to combine with hydrogen to give the hydride, and the same element was taken, it was then combined with oxygen to give its oxide. And depending on the formulas of this hydride and oxide so formed, he classified his elements. Let's take the example of sodium. Sodium, Na is its symbol. When sodium combines with oxygen, it gives an oxide, and the oxide is Na2O. And when sodium combines with hydrogen, you get a hydride, and the hydride is NaH. Similarly, when you take potassium, that is K, symbol K, and when potassium combines with oxygen, you get K2O, potassium oxide. And when potassium again combines with hydrogen, you get a similar KH. So then he concluded that any of this, like sodium, potassium, say we call it R, combined with oxygen, you get R2O, and with this R combined with hydrogen you get RH, the hydride. He put all such elements in the first group. Let us now examine the first group of Mendeleev. This is the first group. Here is its oxides, and this is the formula of the hydrides. So the oxide formula of all the elements is R2O, and the hydride formula is RH. We start with lithium. We know the formula of lithium is Li2O, and the hydride will be LiH. Next, you take up sodium. Sodium oxide Na2O, hydride NaH. Then you take potassium. Potassium K2O is oxide, hydride is KH. And in this way, all these elements having an oxide R2O and hydride RH was put in group 1. Let us take up group 2. So here is group 2 with all its elements. And if you see here in group 2, the oxide is RO and the hydride is RH2. We'll take up the first element, say magnesium. Oxide of magnesium we know is MgO. So probably the hydride would be MgH2. Then we take calcium. Calcium CaO oxide, and the hydride, if you were to form, would be CaH2. So these elements form similar oxides and hydrides, and hence they were put in the same group. Now for group 3. This is group 3. And in this group 3, here are the oxides and the hydrides. The oxide is always R2O3 and hydrides RH3. We take up, say, aluminium, which we are so familiar with, and aluminium oxide is AlO3 and the hydride will probably be LH3. So all elements having this formula of oxide and hydrides were put in group 3. In this manner, he classified all the other elements also. In group 4, the oxide was RO2, hydride was RH4. Then in group 5, group 6, this was the formula of oxides and hydride. Group 7, formula of the oxide and hydride. And just like the modern table, Mendeleev's table also had periods and groups. So there were groups were the vertical. There was group 1 here, 1, 2, 3. These were the groups, the vertical columns, and then we had the periods, which were the horizontal. Like here's one period 1, period 2, period 3, period 4, and period 5. We'll learn the characteristics of Mendeleev's table. The first point is it had 8 vertical columns called groups. So here we can see 8, 1, 2, 3, 4, 5, 6, 7, 8 columns. So Mendeleev's table had 8 groups. The second point, it had 7 horizontal rows called periods. In the 7 rows we can here see this is period 1, period 2, 3, 4, 5, 6. Yeah, so there are 6 periods, not so put 6 here. So he had 6 periods, the horizontal rows called 6 periods. Another characteristic is closely observe each group. Like group 1, it is divided into 2, A, we have all these elements A and all this B. So each group was further divided into A and B. So here A, which were called the normal representative elements, and B, the transition elements. However, the last three, that is the eighth group, which is here, was divided into three. You had 1, 2, 3 subgroups. Group 8 contains 9 elements, 3 sets each containing 3 elements. So here we have 9. This is 1, 2, 3. One set, 1, 2, 3, 1, 2, 3. So the 8th group had 3 subgroups. So every group had 2. It was A and B. However, the 8th group had 3. So you need to learn these characteristics of Mendeleev's. Just to repeat again, he had 8 groups. Here 8 groups, 6 periods. Each group was further divided into A and B. A were called the normal elements, B were called the transition elements. However, the 8th group was divided into 3 sets. And he had 9 such elements. We'll now go into the achievements of Mendeleev's tables, or the advantages of Mendeleev's table. One important advantage was the inert gases. Now, we know what were inert gases. Examples of inert gases like is helium, argon, neon, krypton, and so on. When Mendeleev made his table, the inert gases were not discovered. And why were they not discovered? Because first they were inert, they did not react, and they were in very low concentration in the air. So they were not even known. Inert gases were not discovered because of these 2 reasons. They were inert, they were unreactive, they did not react with other elements, and they were in low concentration. So Mendeleev did not include the inert gases in his table. But when the inert gases were later discovered, they fitted his table so well. See here, they fitted in this column out here without disturbing his table. That was one of the achievements of Mendeleev's table. Another achievement is he left gaps in his table, like you can see out here. These were the gaps he left. And he boldly predicted the properties of these elements. He said elements will be discovered which will fit into these gaps. And the elements discovered were scandium, gallium, and germanium. And they fitted exactly in those gaps that Mendeleev had predicted. Like this first gap, this gap that he left, he called it boron. And later an element was discovered which they call it scandium. And the properties of scandium exactly fitted the properties of boron. Here. Then the second gap. This second gap, he called it aluminium, and predicted the properties of aluminium. And later when it was discovered to be gallium, and the properties exactly matched aluminium. And the third gap, this is the third gap, he named that gap silicon. There was no element discovered then. He named that gap silicon, and he gave the properties of that element before it was even discovered. And when they discovered it, they found it was germanium. And germanium fitted exactly the properties of silicon. And in this manner, he left many other gaps also. All these gaps that were left, the properties could be predicted and they fitted into his table very well. So if you look up at the table here, you have the Dobinius triads which also fitted in his table. Here see the Dobinius triad, this is one Dobinius triad, right? Here is another Dobinius triad, calcium, strontium, barium, all in one group. Then these are the known elements. The ones in the green are the known elements, and these were the unknown elements, the one in the purple. And all these unknown elements which were later discovered fitted in his table without disturbing the table. This was the achievement of Mendeleev's table. Let's go over again the merits of Mendeleev's periodic table. This is given in your notes which you have to study. So the first merit was he made a systematic study of elements present at that time, 63 elements. Elements were arranged in groups and periods. Elements in a group had similar properties. If the property of one element is known, the properties of others also could be predicted. Then the second, there were some doubtful atomic masses of some elements like beryllium were then corrected by his table. Then prediction of elements and their properties. He left gaps in the table and boldly predicted the properties of these elements. Later, when these elements were discovered, the properties matched. And the last and a very important merit, noble gases were discovered later, and they fitted the table without disturbing the existing order. We'll go to this table given in your textbook on page 84. And here it clearly shows how he predicted the properties of the elements. When it comes to aluminium, he said the atomic mass would be 68. And when gallium was discovered, the atomic mass was 69.7. Then he said the formula of his oxide would be E2O3. But when gallium was discovered, its formula was Ga2O3. Then the chloride, he said, would be ECl3. And when gallium was discovered, it was GaCl3. So his predictions were very close. Thus we see from the table that the properties of these elements keep repeating after a fixed number of elements. And hence Mendeleev formulated a periodic law. And this periodic law states that the properties of elements are periodic functions of their atomic masses. What does this statement mean? If you arrange the elements in increasing order, elements with similar properties keep repeating themselves after equal intervals. So if elements are arranged in the increasing order of atomic masses, properties keep repeating. They keep repeating after fixed intervals, after fixed number of elements. We'll now learn into the limitations of Mendeleev's table, or the disadvantages, or the places where he went wrong. One is the position of hydrogen. Mendeleev placed hydrogen in group 1. So the position of hydrogen in Mendeleev was group 1, period 1. But however, he could not explain why he places in that position, because hydrogen showed properties like that of alkali metals. It resembled alkali metals. just like the example of sodium. Hydrogen combined with chlorine to form HCl. Sodium, which is an alkali metal, also form NaCl. Hydrogen combined with water to form H2O. Alkali metal like sodium also formed Na2O. And then hydrogen combined with sulfur to form H2S, and sodium also formed Na2S. So hydrogen resembled alkali metals, which means it had to be put along with the alkali metals, which he did. He put it along with the alkali metals. But hydrogen also showed properties of halogens. Just like halogens. Now, who are the halogens? Halogens is like chlorine, bromine, iodine. These are halogens. Just like halogens, halogens exist in diatomic form. Diatomic means like Cl2, Br2, and hydrogen also exists in diatomic form, that is H2. Then it also combines with metals and non-metals to form covalent compounds. Halogens form covalent compounds, and hydrogen also forms covalent compounds. So it showed properties very similar to halogens, and hence he had to put it also with the halogen. He should have put it also here. So he could not explain why he put it with alkalis and not with halogens. Although hydrogens showed properties of alkali and also properties of halogen. It showed both the properties. So this was one of the limitations of Mendeleev. Isotopes also posed a problem for Mendeleev. And why did isotope pose a problem? First, we must remember that isotopes were discovered way after Mendeleev's table. When they were discovered, they could not find a proper position in his table. Take the example of chlorine. Chlorine has two isotopes. Both have same atomic number 1717. However, the mass is different. One is 35 and one is 37. So since they have different mass, they will occupy different positions, because the table was according to the atomic mass. So they'll have different positions, but they have same chemical properties. Isotopes have same chemical properties. So if they have same chemical properties, they should occupy the same position. This Mendeleev could not explain. His table could not explain this. They have different, this is 35 and this is 37. They should have had different positions, but same chemical properties. So both these were put in the same slot, Cl35 and chlorine 37, although they had different atomic masses, were put in the same slot. So isotopes posed a challenge to Mendeleev. Another one example of carbon. Carbon has got two isotopes. Both have same atomic number 6, but one is 12 and one is 14. And they have similar properties. So because they have similar properties, they have to be fitted in one slot, in one box. So carbon 12, carbon 14. This is carbon 14. They have to be put in the same slot. So that means different elements, different atomic mass in the same slot, which was not proper according to Mendeleev's table. Mendeleev's table was based on atomic masses. Different atomic masses should have been different slots, but both these showed same chemical properties. There's another limitation was the irregularity in the pattern of the atomic masses. Compare the first element and the second element, helium and lithium. The difference of their masses is about 7. Then compare the next two, lithium and beryllium, 6 and 9. Approximately difference is 3. Then we go to beryllium and boron. The difference here is 1. Then if you go to the next, beryllium and carbon, difference is 2. By now you would have noticed that the difference between the two elements is not the same. 12 and 14, approximately 2. Here again the difference between nitrogen and oxygen, approximately 1. So the atomic masses did not increase in a regular manner in going from one element to another. So it was not possible to predict how many elements could be discovered between two elements. So there was an irregularity in the increase in atomic masses. The atomic masses did not increase regularly. And so you could not make out between two elements how many more elements would have been discovered. Now just observe cobalt and nickel. You see cobalt has atomic mass 58.93 and nickel has atomic mass 58.71. What should have happened? Nickel should have come first, 58.71, then should have come cobalt, 58.93. But he put cobalt first and then nickel. See here, he put cobalt first. And why did he put cobalt before nickel? Because cobalt had properties similar to these elements and nickel had properties similar to these elements. So he disturbed the order of the atomic mass to make sure that cobalt came along other elements which had similar properties and nickel came along other elements that had similar properties. However, all these irregularities were then resolved in the modern table, which we'll see in the next slide. So in the earlier slide we saw that the Mendeleev's table had certain irregularities which were resolved in the modern table. Now we'll discuss why were they resolved in the modern table. The first basic reason is the modern table was based on atomic number. Remember, Mendeleev was based on atomic mass. That was the main problem, was based on atomic mass. Then comes, what is the difference between atomic number and atomic mass? Atomic number is number of protons, while atomic mass is protons plus neutrons. Then why did Mendeleev not base his table according to atomic number? Because protons, neutrons were discovered way after Mendeleev had put up his table. The Rutherford's model of an atom came later. So earlier it was believed that atom was indivisible, so they only took atomic mass. They did not take atomic number because the discovery of protons and neutrons was done later. So to repeat, the discovery of protons, electrons and neutrons was made later. Hence Mendeleev did not base his table on atomic number. However, later Henry Moseley in 1913 showed that atomic number of an element is more fundamental than its atomic mass. And then we had the modern table which said that properties of elements are periodic functions of their atomic number. So this is the modern periodic table which you will need to learn. An explanation of this is when elements are arranged in increasing order of their atomic number, the properties repeat after fixed number of elements. That is why the word periodic, which repeats again and again after fixed amount of time or fixed amount of intervals. We saw that Mendeleev could not give a proper position to hydrogen. Now, why did the modern table give a proper position to hydrogen? In the modern table, hydrogen occupied group 1, period 1. Why group 1? Because it has one valence electron. And why period 1? Because it has got one shell. So the modern table could give a proper reason why hydrogen was put in group 1 and period 1. Next was position of isotopes. Mendeleev could not give a proper position to the isotopes, but modern table solved this problem. Now look at the isotope, for example, chlorine. Chlorine has got two isotopes, chlorine 17, chlorine 17. One has got 35, one has got 37. Now because the modern table is based on atomic number, see this is 17 and this is 17. So both will occupy the same position 17. Because atomic number is 17. So Cl35 and Cl37 occupy the same position. So the problem of isotope was solved in the modern table because it was based on atomic number. All isotopes, let's take another example like that of carbon. Carbon 12, we just have to put 6 here, carbon 6 and carbon 6. Two isotopes, one 12 and one was 14, all also occupied same position. Why same position? Because both had same atomic number. Earlier we also saw how cobalt was put before nickel, although nickel should have been put first and then cobalt, but he could not explain why. See, cobalt had got an atomic mass much more than nickel. Nickel should have been placed first with 58.71 and cobalt was 58.93, but he placed cobalt first and nickel. We discussed this earlier. But when you come to the modern table, see the cobalt is fixed first and then nickel. And this you could explain because cobalt has 27 and 28. So definitely 27 would come first and then 28. So when you place it according to atomic number, the things fell in place rightly. But if you did it according to atomic mass, there was some discrimination, there are some limitations to the table. So this clearly goes to show that the atomic number was more fundamental property than atomic mass.